All right, another equation that we can use to solve for motion in these types of problems when we're experiencing uniform acceleration is the second kinematic equation. And the derivation for this is, or where this equation comes from, is somewhat complex. For many beginning physics students, application of this is sufficient, and then eventually you'll be able to determine where it comes from. The derivation for this is on this page. We know that velocity is distance divided by time, or displacement divided by time, so displacement is velocity times time. We also know that displacement, which is our final location minus our initial, is equal to the average speed times the time. If we solve or distribute the 1/2 through and then substitute an equation in for time, ultimately in the big picture we're going to end up with our second equation for displacement, the first one which was derived and used previously. The final location depends on where you start, how far you move due to having initial velocity, and then how far you would move due to having acceleration. And if we look at this, this will give us a position function which kind of goes beyond what we need to know. That is curvy. And we know the slope of our position function is the acceleration, or is the velocity, and the slope would be changing as time goes on. But enough of that. That's not the main focus. It's a quadratic formula. Our main focus is to apply this. If we're interested in finding displacement, this equation can also be born from our velocity time graph. We know that the area under the curve with respect to the axis is going to be velocity times time, and that area is displacement. So this would be displacement for an object experiencing a constant velocity, a zero acceleration because the line is flat. And if we apply another situation, the area of this one, and if you look, it's a triangle, it would be 1/2 times the base times the height, 1/2 times the base, which is time, and the height, which is velocity, will give us this formula, 1/2 times time times delta v. We also know that delta v is a times t, so when we sub it in, 1/2 times time times delta v, at is 1/2 at squared. So the displacement is 1/2 at squared in this case. Marrying the first case constant velocity with non-constant velocity, we end up with two geometric shapes, a rectangle which has an area vt, which is the displacement, and a triangle which has an area of 1/2 at squared. And if we add v naught t to 1/2 at squared, these two terms, it will give us the displacement due to moving with a constant speed plus the acceleration, and then we can account for our starting position with that term. So it's the equation. If I circle this in, let's say, a different color, once again, x equals our starting position plus vt plus 1/2 at squared. And the main goal is to apply this and use it to make predictions of motion. So in this problem, what we're going to do is to have an airplane starting from rest, so its initial speed is 0, and it accelerates at a rate of 3 for some time before leaving the ground. The question is, how far did it go along the runway? Let's make another assumption. Its initial location is 0 meters, and we just pick that location. That's where we start. We know that the displacement we experience will be equal to our starting location plus the displacement due to having speed to begin with. That would be v naught t plus 1/2 at squared. Now, quite a bit happens that makes this problem easy. First of all, we start off with at a location of 0, so our initial location is 0. That term goes away. We also start off with an initial speed of 0, so that term goes away. So it leaves us with one term. The displacement will be equal to 1/2 a times t squared, both of which are known, a and t. And when we solve, the displacement will be equal to 1/2 times what the acceleration is, 3 meters per second squared, times what the time is, 30 seconds. Oh yeah, that's right, we're finished now. Almost. 1/2 times 3 times 30, that's the displacement. I forgot to do one thing. We have to always square that. That's the most common mistake. And if we looked at the units, we'd end up with meter seconds per second squared. It wouldn't work out. We can't forget to square the time, 1/2 AT squared. So 30 squared will end up being 900. That's 30 times 30. Seconds squared are seconds times 3 meters per second squared times 1/2. So if we do 1/2 times 3 times 900 and meters per second squared times second squared will cancel, and when we reveal the answer, the displacement is 1,350 meters. So if we were designing a runway that had to account for the acceleration needed, and it takes 30 seconds for this plane to leave the airway, we'd have to design that runway at least 1,350 meters long. You're probably going to make it longer than that, maybe even 2,000 meters, just in case you have planes that experience different accelerations or have different flight needs. So again, we can solve for the displacement or how far we moved along the runway using this brand new equation.